lecture. I don't know how you could tell whether it's being recorded or not, but I forgot to start the recording. There's a question, are the concepts on the review we should go over for true and false questions? Uh, the, I'll try to remind you of the high points for the concepts, but you should study your full lecture notes. There'll probably be other concepts that we're not going to talk about today. So just learn everything, that's the usual way. Okay, so we start off with a Born-Oppenheimer approximation. Basically, you remember this says that electron motions are so fast that nuclei appear to sit still. And so we're only interested in electron energies when we talk about molecular bonding. And so our bonding energies are basically always the energies of what the electrons have. When we go to molecular vibrations and rotations, then we're looking at the motions of the heavy nuclei. So whenever we get to the heavier motions, then the electrons are going to appear as electron density about the nuclei, or what I like to call as fuzzballs. So here was basically the approximation. The overall wave function can be separated into a heavy part, the nuclear part, and then the electron part. And the nuclear part, as we'll see later, it's a combination of vibrational and rotational energies. But when we talk about bonding, we look at the electronic part. We started off, we looked at the potential function for the H2 plus molecule. Make sure you're able to write these potential functions for any system where you have plus and minus charges. If you have a plus charge attracting a minus charge, then you get a minus E squared over the bond distance or the distance between them. In this case, it's the electron to the nuclear distance. So be able to write a potential function like this. What the Born-Oppenheimer approximation says, if this is our total Hamiltonian, so this is the kinetic energy part plus the potential energy part, it has kinetic energy terms from the electron and both of the protons that we have in H2 plus. Born and Oppenheimer say throw out the second and third terms here. The masses of the protons are heavy, so that makes these even smaller. The motions of the protons, the nuclei, are slow, and so these derivatives are slow. So basically, when we solve the quantum mechanical problem, this is what we solve for the Hamiltonian. But notice that the potential energy still stays the same. I do point out that when we go through the mathematics of looking at this, as far as the electron is concerned, it thinks of the bond distance between the two nuclei as being a constant, simply again because the electron motions are so fast. Okay, as always, we use the variational theorem whenever we cannot get exact solutions. So this says we guess a reasonable wave function, we apply this equation, and whatever result we get, the calculated energies cannot be less than the real value. So typically they're larger. And so what we try to do is get the best guess that we can by minimizing this calculated energy. And those are typically the results that we look at. So with this background, we go into our molecular orbital linear combination of atomic orbital method. And we learn to see what the best combinations are by applying the variation theorem. The basic model that you've seen over and over and over again, when you combine like signs of the wave function, plus to a plus, you get a nice bonding orbital. If you have opposite signs, like a plus wave function going into a minus wave function, you get an anti-bonding orbital. And the typical reason for this is you're going to have to go through a value of the wave function equal to 0. When the wave function is 0, its probability psi squared is 0. And so you're going to have a region of no electron density. And then the positive nuclei will repel each other. Okay, so we started smushing orbitals together. We first combined the 1s orbitals. So in this model here, we're doing homonuclear diatomics. We know exactly what the atomic orbital wave functions are. So this we solved when we solved the hydrogen atom problem. And so here what we do is we take this function for the electron on nucleus A, add it to the electron on nucleus B. Pictorially, it winds up giving us a molecular orbital like that. So plus wave function going to plus wave function, and we can have a plus wave function in the entire region. Whenever we start from 2 atomic orbitals, we have to wind up with 2 molecular orbitals. The second one is antibonding, and this is where the wave function changes sign. So we're combining a plus function to a minus function, and our orbital looks like this. And there's going to be a region in the center where the probability is 0. Very close to that, the probability is very small. So we played around with nomenclature a little bit, but we finally settled that we're going to call this lowest energy orbital 1s sigma, and then we called the corresponding antibonding orbital 1s sigma star. And so that led to our Aufbau method, and we'll talk about that later. When we apply the variation method, then we come up with a formula for the lowest energy orbital, which looks like this, and then one for the antibonding orbital. J and K are complicated integrals. They're both negative, and so they take the energy of the molecular orbital lower, which is good. We want to get the lowest energy possible. The plus E squared over RAB is a repulsive term. So we would like to keep the R at a reasonable value, not make it small where the potential energy goes up to infinity. E sub h comes out to be the energy of the hydrogen atomic orbital, and it's a nice reference point. So if we can take an electron from a hydrogen atom, put it into the H2 plus or H2 molecule, and if we can take it to lower energy, then we have a more stable system. So here are graphs of the bonding orbital and the antibonding orbital. The molecule, as I like to say, is smart, so it finds its lowest possible energy. It picks this equilibrium bond distance, and so that's what you're going to have for the molecule. 2 electrons will go to this energy, and for H2 or H2 plus, no electrons have to go into the antibonding energy. The most important integral for bonding is the resonance integral. And the thing to note that it's represented by having probability on both nuclei at the same time. So we take 1sa and 1sb as part of the situation. So the electron is spending time on both nuclei, and it's being attracted by one of the nuclei. So this gives us about 90% of the stabilization. The J Coulomb integral helps a little bit, 10%, and basically indicates the electron is on one of the nuclei. First integral here, it would be on nucleus A, but then it's attracted by the other nucleus. But mathematically and physically, this is not as significant to create bonding as the K integral. Okay, then we learned the Aufbau scheme, and keep in mind that you have a switch in order. If you're up to 14 electrons, the 2p pi electrons are below the 2p sigma. So this would be the scheme for the first 14 electrons. After you get past 14 electrons, starting with N2, for example, the 2p sigma orbital falls below or comes before the 2p pi orbital. And keep in mind always when we do the 2p pi orbitals, we can write 4 there for the 2 orbitals. But we should always remember that there's an x component and a y component, whether we're talking about the bonding orbitals, as in this case, or the antibonding orbitals, as we have here. Bond order is 1/2 the difference between bonding and number of antibonding electrons. If you get unpaired electrons, you have paramagnetism, and it's easily measured, so we know which of these molecules come out to be paramagnetic. I'm not showing you the diagram, but go back to your lecture notes, look at the diagrams for lithium hydride and hydrogen fluoride, and I've tried to indicate to you where the electronegativity comes from. If a molecular orbital winds up having more contribution from one atom or another, then the electrons in that orbital will tend to give that particular atom a minus charge. So in the case of HF, we had the 2p orbital of fluorine being lower in energy than the 1s orbital of hydrogen, and the molecular orbital formed then was primarily made up from the fluorine atomic orbitals. And since that was the case, then the electrons spend more time on the fluorine, and you have a partial negative charge on fluorine, partial positive charge on the hydrogen. I showed you some diagrams of polyatomic molecules for water, methane. So again, go back to the notes and look at that. Both in the case of lithium hydride and methane, I showed you that hybridization could be useful in trying to understand what the bonding combinations were. But I also pointed out you could totally ignore hybridization. It's not a necessary concept. It's a human artificial creation. It's not something the atom actually does. Okay, so, I have a question. Why does O2 and other molecules have two unpaired electrons? We talked quite a lot about that in class. Look at the electron scheme. There's a diagram for the water. For the water molecule, we basically wind up, it finishes up at 2p pi 4, 2p pi star 2. And so when it's 2 and there are two orbitals to put the electrons into, Hund's rule says you put one into the X-type orbital and one into the Y-type orbital. So that kind of question you should be easily able to answer. It's a basic concept that we have from doing the Aufbau scheme. So there will be an Aufbau question on the examination. Okay, so then we spent quite a lot of time on Hückel calculations. And so let me see if I have that. Okay, so I strongly recommend going back over the notes about Hückel calculations. You're probably going to be asked to write a secular determinant of the type that I have on this page. I will probably give you a bunch of energy levels that come out of that pi system. I'll want you to draw an energy diagram, put in the electrons. I might want to ask you about what is the pi bond stabilization energy. So be familiar with how to set up the Hückel problem. So on this page, we did several examples. Benzene, this three-membered ring triangular model, and appreciate the fact that when you put electrons into antibonding orbitals, that weakens the bonding. And so I could ask a concept question, for example, how do I make C3H3 plus more stable? And the answer would be remove this electron and make C3H3 plus, for example. Okay, so that was Hückel calculations. We then talked about spectroscopy, and someone in this class requested that I send everybody some practice problems that are in the lecture notes. And so I did that yesterday, I think, so you should have gotten those. All of them are also in your lecture notes, but I will go over some of those after I finish going over this part of the review. Okay, general aspects of spectroscopy. Keep in mind that we can have either absorption or emission. We always have conservation of energy. If a photon is absorbed with energy h nu, then the molecule gains that amount of energy by going to an appropriate quantum state. If you put in the wrong frequency, your molecule is not going to absorb. So whenever you took infrared spectra in organic labs, you saw that there were specific absorption bands for different vibrations that you had of that particular organic molecule you were looking at. If you go from a higher level to a lower level, that's emission spectroscopy. It is still conservation of energy. You start off with extra energy because the molecule is in an upper quantum state, in a so-called excited state. And when it falls back down, it's again delta E is equal to h nu, and that photon is emitted, and the molecule has that much less energy. We also talked about intensity, and intensity depends on two things: population, and population is given by this formula. So number of molecules in some upper state I as compared to the lower state N0 is equal to a degeneracy term times a exponential term. The G sub I most of the time doesn't matter, but as we saw for molecular rotations, for diatomic molecules, it matters a lot. You have a 2J plus 1 degeneracy, and from that, we saw whenever we looked at the rotational spectra coming from different levels with different quantum numbers J, the intensities would go up for a while because the degeneracy would go from 1 to 3 to 5 to 7 to 9 and so on. The exponential term says as you go to higher J levels, the population goes down. It also says if you increase your temperature, you drive more molecules into upper states. In the last part of our course, we're going to talk about thermodynamics and statistical mechanics, and we're going to see that energy gets distributed over all these quantum states, and the temperature then affects what these populations are. Intensity also depends on the dipole or the transition moment integral, which has the dipole moment in it. And notice it's got both the initial and final wave functions of the states. So you start from state I and you go to state F, initial state to final state. The M term is a dipole moment operator, but this is where all the selection rules come from. Later, we say delta J has to be +1 for rotational transitions, delta V has to be +1 for harmonic oscillator type transitions, and so on. And it's the transition moment integral that gives rise to that. I introduced you or told you again or reminded you again about Raman spectroscopy. Basically in Raman spectroscopy, you shine a laser in. Most of your photons come out at the same frequency as Rayleigh radiation. It's not shown on this diagram, but about 1 photon in a million changes frequency by landing on a higher level. So you can see the energy coming out is a vibrational frequency less than what was put in. So we can collect nice vibrational spectra, or if we like rotational spectra, by looking at the shift in frequency. So whatever loss in energy we have, that goes into exciting a vibrational or rotational state. And as we saw, Raman spectra operate under different selection rules. For infrared, we had to have a dipole moment change for vibrations. For Raman, we say it's a polarizability change. And basically that means the vibration has to change the shape of the molecule as it takes place. We talked briefly about line widths. We don't see extremely sharp bands in our vibrational or rotational spectra. One reason is when we're looking at vapor phase molecules, some of them are flying towards us, some are flying away from us. If they fly towards us, they appear to have higher frequencies, just as we know about the Doppler effect for a siren on a fire truck, for example. If something is moving away from us, then the frequency goes down. We also saw there's a second reason. This comes from the Heisenberg uncertainty principle, and it has to do with lifetimes. So excited states of electronic transitions have very short lifetimes, and so they tend to have broad bands. If you have closely spaced quantum states, their lifetimes are usually a lot larger, and then the uncertainty in that energy level tends to be a lot less, and you don't have nearly as broad a band when you look at it. Okay, then we went over to rotational spectroscopy, and much of our discussion and what you can expect to see on your exam has to do with diatomic molecules. These are not the most important molecules, but they're the easiest to understand, and the same kind of concepts carry over when we look at polyatomic molecules. So in our diatomic molecule of rotation, we first noted that rotations are about 100 times slower than vibrations. So that means we can look at the bond that we have as being rigid. So the molecule is actually vibrating 100 times every time the molecule rotates. And so the rotating molecule can think of just as an average value of those 100 vibrations that it sees. We defined a reduced mass, product of the masses divided by the sum of the masses. When you do problems, make sure that you remember to convert it to grams by dividing by Avogadro's number. Moment of inertia we saw is equal to the reduced mass times the bond distance squared. So you have a problem that's going to be related to applying that formula. We solve the Schrodinger equation. We find the energy levels come out looking like this. And on the cover sheet of your exam, I will give you the relationship between rotational constant and moment of inertia. In the notes here, I put this in kilogram meters squared, but as I've been telling you, I don't like working in kilogram meters. So I'm going to give this value as 10 to the minus 40th over gram centimeters squared. And since the calculations are done in units of centimeters minus 1, that's a lot handier rule to look at. Okay, so here, I'm not showing the spectra, but I see pages R4 and R5 to look at the spectral transitions. So let's go back over here. These aren't pages R4 and R5. Let's go back to those. I think this is R4. All right, so make sure you understand that we have talked about two kinds of spectra for vapor phase molecules. This we call pure rotational spectroscopy. So when we look at pure rotational spectra, we see something like this at very low frequencies, bands for HCl at 21, 42, 63, wave numbers, all 2B apart. And so these are the transitions that we see in the pure rotational spectra. And here are then the pure Raman spectra with delta J equal to 2. On the right, these are infrared, delta J equal to +1. For Raman, it's delta J2. So make sure that you understand this part. Okay, so that's my reference to that. In the infrared spectra, you're going to see bands 2B apart. In Raman spectra, the first band is going to be at 6 times B, and then after that, they're going to be at 4B separation. So the first band is at 6B, then 10, then 14, and 18, and so on. In the broad picture of things, this is not something that's going to help you get a job at DuPont or Dow or something. But hopefully all of you will retain in your mind that there's an order to what one sees when you're taking spectra and getting structures and so on. In polyatomic molecules, it tends to get more complicated. An important part that I was just telling you is to remember the degeneracy. These rotational levels each have a degeneracy of 2j plus 1. And this comes from the fact that every j component has an m sub j going from plus j to minus j. Very similar to what we had for atoms. When we had L equal to 2, m sub L could be plus 2, plus 1, 0, minus 1, minus 2. And that's what you had for d orbitals. You got 5d orbitals. When j is equal to 2, you have 5 degenerate rotational levels at that same energy. And so that increases the population of molecules at that energy. And so your bands wind up being stronger. We talked very briefly about polyatomic molecules. The key feature to understand is most molecules are asymmetric tops. They have 3 different rotational constants, A, B, and C. And so you can get 3 pieces of structural information on a molecule. For many, many systems, you can use isotopic substitution. Organic molecules with carbon. Carbon is naturally about 1% carbon-13. So you already have isotopic forms of these molecules in there. It's also very easy to put deuteriums in place of hydrogen atoms. Those are hydrogen atoms of mass 2. And so you can get lots more rotational constants from which you can calculate structural data. So what I showed you is for water, we only needed 2 parameters to understand the structure. We had 3 rotational constants. For hydrogen peroxide, we needed 4 parameters. And so you needed a second isotopic form, so you could have 6 rotational constants to determine those 4 parameters that you have. Okay, then we talked about vibrational spectra. Understand what the difference is between the harmonic oscillator and the real molecule. The real molecule, when you pull the 2 atoms apart, the energy approaches the dissociation energy, and the 2 atoms just totally come apart. We use the harmonic oscillator model, even though it's wrong at large R values. The harmonic oscillator would tell us the potential energy goes to infinity as R gets large, but in fact it dies off. But we use it because the real molecule and harmonic oscillator curves are very similar at the bottom part of the potential function. And this is where we see the transitions for the vibrations. Most of the time, we're going from the lowest quantum state to the first excited quantum state. Keep in mind also, in vibrational levels, I didn't draw it on the diagram, you have a 0-point energy, and that's 1/2 the vibrational frequency. That comes from this 1/2 in this energy formula here. And the vibrational frequency is given by this formula here. In this review, I didn't write it, I think, oh no, I did. When you want to do calculations, up here, this formula has frequency in seconds to the -1, but we're going to typically work in centimeters to the -1. So then I put a bar over the nu. And if I want to calculate then the force constant, then I need the reduced mass in grams, the vibrational frequency in centimeters to the -1, speed of light in centimeters per second. So make sure you practice doing a problem calculating the force constant from a frequency, or if you know the force constant, calculate what the frequency comes out to be. As I've told you in class, the biggest problem most people have with understanding some of this is from the vibrational and rotational spectra. I try to argue that this is just a matter of subtraction and addition. Figure out the energy of the upper state, which is the energy you get from the vibrational frequency, plus what is the energy of the rotational level you're going to, and subtract from that the energy of the rotational level that you start from. So that's essentially indicated right here. So A transition in rotational vibrational spectra will be the vibrational frequency. This is in infrared spectra, plus the rotational level you're going to. So these J stars represent the quantum numbers of the upper state. And then these J's are the J's of the lower state that you start from. In Raman spectra, you have to remember that the selection rule is either delta J equals 0 or it can be plus or minus 2. So I might go back again to our notes in the lectures. So once I find it, make sure you understand these diagrams. If you can understand these, you shouldn't have any problems with figuring out what a particular transition is. So in infrared, these are the delta J plus 1 transition. These are delta J minus 1. This is the lower vibrational state. This is the upper vibrational state. From the bottom here to the bottom here is the vibrational frequency, nu 0 or nu vibration. In Raman spectra, the jumps are either 0, as shown in here, or plus 2 or minus 2. Okay, and then we only talked a little bit about vibrations of polyatomic molecules. I could ask you how many vibrations a particular molecule has. If it's a linear molecule, it's going to have 3n minus 5 vibrations, where n is the number of atoms. If you have a polyatomic molecule, it's 3n minus 6. The 6 comes from the fact that every molecule has 3 translational degrees of freedom, and if it's not linear, it has 3 rotational degrees of freedom. The 5 comes from the fact there are 3 translations for a linear molecule, but only 2 vibrations. So the review I sent out included electronic spectroscopy. That will not be on the examination. You can expect to see something on your third exam on electronic spectroscopy along with statistical mechanics. Okay, this is what I sent out yesterday. These are in your lecture notes, but there's lots of problems to practice on. So the answers are included, so you can look at those. I won't go over the answers, but so we start with this one. We give you the rotational constant for carbon monoxide. And so first question asks you to calculate the lowest 3 transitions. So you know the first transition is at 2B, the next one at 4B, the next one at 6B. Then you're asked to do the same thing for Raman spectra. The first transition in Raman spectra, as we saw, is 6B, and then the next one is at 10B, and then 14B. I mean, those are the levels, but then the transitions are at 6B, another 4B, and then another 4B. Calculating the bond distance, if you know the rotational constant, from that you calculate the moment of inertia. The moment of inertia is I is equal to mu r squared. You might want to look at problem D. We haven't covered that directly in class, but once you know the bond distance for regular carbon monoxide, you then can assume that its bond distance is going to be the same for the isotopic form. So you have to calculate a new reduced mass to do this. And there's a shorthand way of getting this answer if you take the ratio of the reduced masses. So look at the solutions for this. Problem 2, you're given the vibrational frequency. It's direct calculation to go to the force constant. Again, you need the reduced mass, and you have to make sure the reduced mass is in grams. So practice some of those calculations. You may be carrying some exponents along, like speed of light in there and stuff. So make sure you've got your calculator in shape to do that. Problem B is kind of similar to 1D. You're to calculate what is the vibrational frequency for the carbon-13 isotopic form. The force constant, the bond strength should stay the same, but the heavier mass should lower its frequency. We just looked at what P1 and P2 and R1 and R2 bands are like, so make sure you can calculate those. Similarly, this question asks for you to calculate different bands in the Raman spectrum. So there are a bunch of answers there that you can look at. You're also going to get a Aufbau problem, so make sure you're able to write the Aufbau scheme for any number of electrons, be able to calculate the bond order, be able to calculate whether you have non or unpaired electrons, which would give you paramagnetism. Okay, so we had this diagram in your lecture notes, so study that and make sure you understand it. So someone earlier today asked, why does oxygen have 2 unpaired electrons? The answer is right here. Why does boron have 2 unpaired electrons? The answer is here. So from that, you can tell quite a lot about the properties. You might see a spectrum like this, understand the labeling here, be able to use a spectrum like this to determine rotational constants or vibrational frequencies. Whatever I might not ask you on this exam, you might see again on the final as such. Okay, and then I mentioned that you should be able to do Hickel problems. Here's a practice Hickel problem. You should be able to write the secular determinant. You should be able to draw pictures of the most bonding orbital, most anti-bonding orbital. If I show you something in between, count up the number of bonding interactions, count up the number of anti-bonding interactions. Whichever is more, you can then tell if that orbital is bonding or anti-bonding. So you're not being asked in this course to generate what the orbitals are like, but if someone shows you an orbital, you should be able to tell whether it's bonding, anti-bonding, non-bonding, or such. Here again is another practice problem. Here's the spectrum. You can get the rotational constant from the spacing of the bands at 2b. From that, you can calculate then the bond distance. And then in the last part here, again, you can calculate the force constant from the vibrational frequency. Notice when you do grams, centimeters, second units, you will typically get an answer for a force constant, single digit times 10 to the 5th dynes per centimeter. That's equivalent to 3.81 millidynes per angstrom or 381 newtons per meter. But if you just stick to centimeters and grams, these are the units that you will get. Okay, actually, I think that is everything I might have for the review. What do I have here? Okay, we already went over the Hickel part. So I can take added questions if you like, but do the practice problems. And as I said, study the concepts, a lot of true and false questions. So look at every page in your lecture notes and try to think about what it's telling you. Read the corresponding pages in your book to complement what we've talked about in class. If we didn't talk about it in class, it's not going to be on the exam. And we have a chat question. Someone says, how can we best prepare for the true and false questions? Understand the concepts. If I'm looking at benzene, for example, I could ask the question, does benzene have 3 equivalent pi bonding orbitals? That's the answer would be false. So these orbitals are at an energy of 1 beta unit. This orbital that you all learn about in organic chemistry has 2 beta units. So any page that you pick, there can be a true and false question. A true and false question could be, in Raman spectra, can I see the vibrational frequency directly without a change in rotational energy? And the answer is true, because you can see these transitions. Or I could ask you, O transitions in Raman spectra lower the overall rotational energy of the molecule. So questions like that are what I could ask. So they can be semi-quantitative if you look at it that way. Another chat comment or question? There's a question, how do computer programs do, well, someone says like HF, meaning Hartree-Fock, and I guess my initial reaction was hydrogen fluoride and PM3, use these concepts to determine molecular structure. All of molecular orbital theory is called LCAO theory, linear combination of atomic orbitals. So there are 2 branches of computations, and I've been telling you about the LCAO, linear combination of atomic orbitals. Where I've been simplifying it for you is when I take, for example, a 2s orbital and combine it with another 2s orbital and say then we get 2 molecular orbitals, it is not quite that simple. So even if we're making a molecule like O2, which mostly uses n equal 2 shell orbitals, 2s and 2p orbitals, the 3s orbitals, the 3p orbitals, maybe even the 3d orbitals, they can participate to a small extent to give you slightly better bonding. So in a true molecular orbital calculation, one typically uses hundreds or even thousands of atomic orbitals that can combine to give you the best combinations that you can have. So computers can deal with large numbers, as we all know, so it takes advantage of that. I mentioned that this is only one branch that's done using atomic orbitals. A newer technique is called DFT, density functional theory. And instead of actually using orbital functions, remember for the hydrogen atom, we know exactly what a 1s orbital looks like or a 2s orbital. Density functional theory doesn't actually take mathematical forms of atomic orbitals. They take mathematical functions that are similar to orbitals, but actually work more efficiently for determining the complicated integrals that come out of the computations. Now, I think nobody wants to hear about this stuff before the examination, and none of this is going to be on there. But it's a good question, and I think it's important, actually, that you have a good picture of this, because I'm sure throughout your careers, most of you are going to be using computer programs to tell you about structure, thermodynamic properties, and it's going to be based a lot on things like that. Okay, and have another question. Can you repeat what I said about determining bonding and antibonding interactions in the Hückel method? If you try to match wave functions of the same sign, plus to plus, then it's a bonding interaction. If you put plus next to minus, it's an antibonding interaction. If the 2 orbitals don't touch, it's no interaction. So I think I showed you a few orbitals that were apart, and then they would not have any interaction at all. But go back and look at the pictures that you have in your notes of benzene, butadiene, and you'll see where we have plus, 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 plus. That's a nice bonding combination. But if we have plus going to minus to plus to minus, then that's going to be an antibonding combination. So if we had a lot more time in this course, we talk about symmetry methods and computational methods and ways that you can actually determine what these orbitals look like, and then it'd be a little bit easier to understand exactly why the bonding is the way it is. Okay, well, all of you take care, stay healthy. Do tune in on Friday. We're going to have a lecture on the entire planet Earth.
Professor, you say?
Yeah, did you have a question?
Yes, I did. So on Friday, I just wanted to let you know I'm the Jeopardy chair for the American Institute of Chemical Engineers here at A&M. And on Friday, we're going to have a competition for the regional conference. Me and another student here in this class. So I was working with Ms. Tobeck, which is the administrator for the chemistry department on excused absences, but I forgot to contact the chemistry department because I forgot that this course was specifically from
Okay. Have you sent me an email?
I will do so shortly.
Okay, that'll be fine. And I do encourage you then to look at the recorded lecture, because I think it's very interesting for understanding why we have global warming.
Gotcha. Another question. So there would be, I was worried about the quiz. I don't know if there was going to be a quiz on Friday for that matter.
If you send me an email and if we have a quiz, then you'll be okay.
Okay, thank you. Have a good day.